we're really focusing on presenting our new GigaSeal consumable and a number of different assays that have been developed using single cells, as well as comparing single cell data to ensemble data. So I have a lot of slides. I'll just get started, and I hope I can get through them quickly. So if you have questions along the way, please feel free to type them in, and we'll try to answer them on either at the end of the presentation, or we'll answer it offline afterwards. So first of all, I'll be talking about the differences between single cell and ensemble recording, and I think there's some important things to keep in mind here, as well as some real-world comparisons. After that, I'll go into voltage-gated assay examples, focusing on NAV 18, 17, and hERG targets, and finally some ligand-gated ion channels work using the single-cell consumable. So first of all, this is why we've dedicated a webinar to this topic. We think it's a big deal. We think it's important to be able to both have high-quality data that's the low noise that's enabled by GigaSeal recording, and we think it's also important to keep costs down and to be able to easily replicate substrates. So historically, the automated patch clamp instruments have fallen into one of two categories. There have been ones like IonFlux and Barracuda that have used plastic substrates, but typically achieve lower seals. The advantage of those systems were typically throughput and cost per data point. On the other hand, glass substrates have been developed by Sophion, Nanion, and others, Axon instruments as well, and obviously their biggest advantage was being able to deliver GigaSeal recording. So what I'll be talking about today, though, is what I think is a system that provides the best of both worlds. In other words, we've got a plastic substrate that can now achieve gigaseals, and while I can't exactly talk about the secret sauce, we've worked hard on basically the surface properties and the stability of the surface properties to achieve that. So I'll quickly go through a brief introduction of to IonFlux. That's just 2 slides for people that haven't seen it before. Essentially, we're trying to address two different problems. One is the difficult and expense of doing ion channel screening in pharma, and the training-intensive, low-throughput manual patch clamp that's still widely used in academia. And our solution to this has been to develop a benchtop instrument that has a small form factor, easily expandable, and modular system that can be affordable to both the individual researcher in academia and the screening lab. So basically, the system is based on a well-played consumable that goes into a reader-like desktop instrument, and each plate essentially has a well-played upper, so it's compatible with fluid handling robots, and on the bottom it integrates with a number of different patterns that are made up of fluidic channels. And the fluidic channels basically deliver compound to the recording region. They trap cells, they establish seal, and then go into whole cell. So this is what an experimental pattern looks like. You basically have 8 different compound wells. You have 2 recording channels, and then a cell inlet and the outlet, which collects all waste. An important thing to note here is that a differentiator from other approaches is that we don't actually have electrodes that ever touch active compounds. So basically, compounds travel from, say, C1 through the recording region into the outlet, and there's no electrode in the outlet. The electrodes are in the in well, T1 and T2 wells. Those are the backside electrodes. So that's a nice feature to prevent carryover. Now, here's the crux of this presentation, and that's the development of our single-cell consumable. Basically, in the center of each one of those recording patterns, we have 2 channels, 2 amplifier channels that are connected up to either sets of 20 cells, as you see in the 20-cell ensemble image on the left, or the same amplifier channel can be connected to a single cell. So these two modalities are either an average current over 20 cells or a single cell current, and the consumables use the same exact hardware, albeit with a different gain level for either recording mode. Okay? So briefly, here's how they line up. So if you use 20-cell ensembles, you should expect a seal resistance, an equivalent seal resistance of about 200 megohms. And I'll be talking more about what I mean by equivalent seal resistance. In single cell, you should expect gigaseals, of course, some percent of the time, and I'll talk about our success rates for the different assays and what we see. Everything else is the same, so the same protocols essentially operate for both modes. Now, I wanted to spend a little bit of time so that everybody understands what we mean by equivalent seal resistance and essentially why it's very hard to achieve overall gigaseal recordings in an ensemble format. So what you have here is basically the formulas used to calculate the overall resistance when you're recording from multiple cells in an ensemble format. That's on top here. So the measured resistance essentially is an addition of all the resistances of the different cells in parallel. So you have this 1 over R plus 1 over R plus 1 over R. And essentially what that means is if all of the cells are essentially the same resistance, then the measured resistance is R over N, where R is the resistance of a single cell. So when we report in this presentation ensemble seals, we refer to this R, which is essentially the resistance of a single cell in the ensemble if they were all the same. Now, practically what that means is the resistance is the measured, the equivalent resistance R is the measured resistance in ensemble mode times N, where N is in our case 20, the number of cells. Now, the other thing that happens because of the presence of all these different cells in parallel to one another is that this R ensemble, the equivalent resistance, is actually dominated by the lowest resistance in the set. So what I've plotted down below here is a number of real-life sealing resistances from single cells on the log graph. That's the light blue. And I'm contrasting that with R ensemble, which is the equivalent ensemble resistance for, in this case, for 10 cells. So what you see here is, on the left, we have a case where we get 90% gigaseal. So almost all of the cells are in gigaseal, save this one, which is probably around 300 megohm. Now, in this case, our ensemble is still in the gigaseal regime, albeit only 1.3 gigaohms. Now, the important thing to keep in mind is as you dip below these really high gigaseal levels, your ensemble equivalent resistance is going to go down. So what you have on the right is another, again, real-life examples in light blue of single-cell seals where our sealing rate was only 50%. And you have some really low seals, essentially cells that were either destroyed or maybe we trapped debris like you see in position number 3 here. Now what happens is that here the ensemble resistance is quite low. It's only about 100 megohms. So all that to say is it's not surprising that when you look at ensemble resistances, even though the substrate is the same and you have a decent number of gigaseals, you're actually seeing a lower than gigaseal resistance. And here's a comparison of seals for our NAV18 experiment where we show in orange the single-cell seals, and you see that they're quite robust. First of all, over 85% of them are in the gigaseal regime. This is 1 gigaohm here. And you only have a small tail below that. Now, for the same exact consumable type, so essentially the same set of seal distributions in single cell, the ensemble seals are instead mostly below a gigaohm, and there's only a tail, a small tail above that. So this is exactly what you expect, and I'm just making this point so you should know that we're using the same substrate for both recording modes. It's just that the gigaseal the gigaseal percent is really dependent on the recording mode. So in ensemble, you're not going to achieve a lot of gigaseals. Now, there are advantages to ensemble that are really important. So here's another experiment. This is a ligand-gated ion channel, ASIC, where we're comparing the distribution of channels recorded. And what you should look at here is two things. So first of all, in ensemble mode, every pattern is giving you a response. So you see a distribution, in this case the currents are negative, that's much tighter and where everything is below zero. Whereas in single cell, you see a wider distribution and you also have some non-responders, some cells that essentially don't give any current. So this is the power really of using ensemble recording, is that you can get really high success rates and a lot of consistency in your recording. So here are some actual current comparisons. These are NaV1.8 currents where we look at both single cell, you see that on the left, as well as ensemble currents. Now what you see is that the ceiling is very tight, so these are raw currents and there's no discernible leak here. However, there's quite a bit of distribution in current amplitude. So you have some non-responders as well as robust currents. In ensemble mode, all of the patterns are giving you current, but you have this difference between the two baselines that indicates leak. Okay, so here's just another sort of histogram of the seals we obtained for this NaV1.8 assay. And on the left, I just wanted to plot out the actual seal measurements. So you see that there are really a couple of different populations. There's a majority that are well sealed and then some that just fail. So we've done a number of validation experiments for both the IonFlux 16 and the IonFlux HT to look at the gigaseal success, and we're defining gigaseal as having a measured resistance that is above 800 megohm. And just to be clear, all these resistances that we're reporting are actually not just seal resistance, they're seal plus membrane resistance. So in some cases, in most cases, when you go to whole cell, you're going to get an overall resistance that's lower than the seal resistance, and that's what we report throughout, because that's simply the easiest thing to measure with a step function in voltage. Okay, so again, this is the same type of analysis for NaV 1.8, and we're looking in this case at the current success. And because NaV1.8 typically has not very large currents, we're putting the criteria for success here at a measured peak that's greater than 100 picograms. Okay, finally, this is the same, a similar analysis for NaV1.7. So you see gigaseal success on the left side of the graph with error bars, as well as current recording success. And here we're defining the current as having to be above 300 picograms. NaV1.7 currents are just typically larger than NaV1.8. Now here's a sample IV on a NaV1.7 that's done in single cell, and this is just sort of a sanity check to say, are we seeing the right sort of slope? Are we seeing the right peak value? And I think these are pretty close to what one would expect for high-quality gigaseal recording. Finally, I wanted to go through a couple of different assay formats for NaV1.7. I'm going to do this quickly, and actually most of this data was obtained in ensemble mode. Here you see a recovery from inactivation protocol, and you get the expected time scale here for the secondary pulse. Importantly, people want to look at pharmacology in response to the voltage state. So what we did here is, again, in ensemble mode, we used a train of pulses, and we compared the response during pulse number 1 to the last pulse and to a pulse that's after a holding voltage was applied. So you see the sort of expected shift in this case, the IC50 of lidocaine as you open and close the channel repeatedly. Okay, a similar experiment is shown here for NaV17, and this is just to show, what types of assays are our instruments being used for. Now, I wanted to briefly talk about HERG as well because it remains an important target for automated patch clamp. And I just wanted to go through a number of experiments where we're comparing two different cell lines from two different sources. And so I wanted to start with the raw data so you sort of see what traces look like. This is a single cell, again, gigaseal level recording. So importantly, here's the HERG peak current. This is average and standard error, as well as the recorded resistance, and this is seal and membrane resistance in parallel. So you see that we get robust seals for HERG as well, and we went out to 20 minutes in this case for this control experiment. Now, a different way to look at the data is to look at percent success, and we use the same metrics here. So we're defining gigaseal success as membrane resistance being above 100 megohm, and we're defining current success as being above, having currents above the 20 peak lamp threshold. All right, finally, this is a third set of data of a different HERG line, and you see, again, gigaseal and current success rates. So one thing you should keep in mind is even though these success rates are to be expected for single-cell recording, we can achieve sort of much higher current success rates for ensemble recording, and that's where it's still appropriate to use ensembles. So I wanted to show a little bit of pharmacology as well. So we've got, in this case, a verapamil block. You see the control sweeps being overlaid on the left, and those are for a number of different data points in time, at increasing times. You see that here. And that's contrasted with and a different pattern on the plate. These are overlays of increasing verapamil concentration responses for the same HERG cells. All right, so finally, this is what the current trace charts that you expect look like. And the current trace is basically a plot of current amplitude over time. So for each sweep, we measure the peak current, and that corresponds to one data point on this trace. So this is going a lot longer in time, and you can see here different events going from C1 to C6 that mark all of the compound additions. Now in this particular region of the plate, we used as a control. So you can see that there's no significant change when we add compound. Sorry about that. And on the right here, you can see fairly sharp changes in current upon the addition of verapamil. Of course, verapamil is a fast blocker, so that's what you expect to see. All right, now, a lot of times with plastic substrates, people worry about compounds and sticky compounds and having the right concentration at the cell. So we've done extensive work on this in ensemble mode, and I can talk more about that at the end if you like. But this is just a quick and dirty terfenadine experiment that we did to sort of confirm that we're getting the same type of pharmacology that we get in single cell. So as you can see, we get around 0.1 micromolar for the IC50 of terfenadine. This is pretty good. It's not stellar, but this was again done without taking all the precautions of using large volumes and using long perfusion times and so on, that can actually drive in our system the definitin IC50 value to about 0.03 or 30 nanomole. All right, so finally, another key feature of our system that I think is quite unique is the ability to control temperature. So we've, again, recapitulated here the ensemble experiments where we look at a Herc current and we increase the temperature from ambient to close to 37 Celsius, which is body temperature. And what you should see is a change in kinetics, and that's what this slide demonstrates. It's just a faster decay of the current at 36 C. All right, so now I'm going to switch gears a little bit and start talking about ligand-gated channels. We started out by looking at an A6 cell line. So you can see here, again, for comparison, I'm presenting the single-cell ensemble data, and this is just raw data for 32 recordings. This is half of our HT plate. And that's compared to ensemble data for the same cell line. And what you see is that in single cell, you have really robust seals. They're actually centered around 3.5 gigohms for this cell line. And of course, you do have some failures, and that's this secondary peak up here where the seals are below gigaseal. Now, when you go to ensemble, as you expect, those few low seals drive down the averages, so you get an average of more around 200 to 300 megohms here. Okay, so this is the corresponding raw currents for that experiment. So what you basically see is a really robust response to an injection of a buffer at pH 6. And again, I wanted to point out the fact that while the gigaseal recording, and this is raw data, is really low noise and it has low lead currents, the ensemble recording shines in terms of being able to get really robust and repeatable data and having a current response from all cells. So here, the success rate's about 85% in single cell, but goes up to 100% in ensemble. And here are a few more experimental types of experiments we did with the ASIC lines. What you see is a recovery from inactivation experiment. So I apologize, it's a little bit confusing. These two graphs are not on the same scale. So what you should notice is that on the left, we have one application of ligand at 2 seconds and another one at 5 seconds. You see that the channels haven't recovered. If the second application is at 9 seconds, you get full recovery. So again, this is an important feature of the system. You notice that all of the recordings receive the compound injection at the same time. And that's because we have this microfluidic consumable that allows us to essentially operate synchronously across the plate. So if the protocol gives the command, all of the channels, all 64 channels essentially across the plate can get compound at the same time. And there's no wait time, more importantly, between compound applications. So you can essentially, in this case, we do wait 5 seconds, but you can wait as little as half a second or a few hundred milliseconds between compound applications. Okay. Here's some GABA work as well. So this is single-cell GABA currents. Now, the one interesting thing here is we don't really obtain a lot of R measured in the gigaseal regime with this particular cell line. And although I don't know this for sure, our suspicion is that the membrane resistance is actually significantly lower for the cell line, and you have conductances that open up when you go into whole cell. So again, the whole cell measured resistance is usually below gigaseal, and the gigaseal success rate in this case is only about 20%. So With that, I'd like to summarize. I think that we're roughly on time, and I'll try to address some of the questions that have come up. The most important take-home from this webinar is that we can routinely produce gigaseal data using our plastic microfluidic substrates. I tried to explain why, despite using the same substrate and the same high-quality seal on an individual cell level, the equivalent seals for ensemble recording are typically below a gigaohm. The gigaseal success rates we see are in the range of 60 to 85%, and I've provided some real-world data to support that. The assays we validated, as you saw, were NAV 18, 17. We've done a lot of work with HERG, and we've done some work with ligand-gated ion channels as well. So to conclude, I think if I had to say it in one word, I think the biggest advantage of the IonFlux system is its flexibility. So with the same device, you can obtain gigaseal recordings from single cells. You can also obtain really high consistency ensemble recordings, and that's switching between the modes is as easy as using a different substrate. Now, the other differentiators are, of course, the continuous perfusion and the synchronous operation. I think that becomes really important when you're looking at ligand-gated ion channels, and I think you really need the continuous perfusion if you want to make sure that all of your agonist gets removed between applications and have a really clean recovery. That's actually essential for a number of different targets, like NMDA as an example. The other thing that continuous perfusion does is it gives us the ability to apply compound throughout the experiment. We can flow from the same compound source for the duration of the experiment. So when it comes to pharmacology and sticky compounds, that really helps in terms of being able to overcome some of the compound loss through continuous perfusion. Finally, I think temperature control is another unique and important feature, and I hope I've demonstrated that. So with that, I'm going to conclude, and thank you for your time.